Hello everyone, myself Ajay CK, working as Assistant Professor in the Department of Mathematics, Maharaja Institute of Technology, Mysuru. Today I am going to explain a very important topic which is frequently used in the Department of Electrical and Electronics, that is Z transformations. Z transformation is an important tool to solve differential equations. Z transformation is used to convert discrete time domain signal into discrete frequency domain signal. It has a wide range of application in mathematics and signal digital data. It is mainly used to analyze and process digital data. For example, to analyze zip files, MP3 and MP4 songs, JPEG format images, we can make use of Z transformation. In the last few videos, we have already learned about Laplace transformation and Fourier transformation. Then obviously a question will rise that what is the difference between Fourier transform, Z transform and Laplace transform? If all the transformations are same, then why we need Z transformation? The Fourier and Laplace transformations are continuous transforms of continuous function. Z transformation is an essential discrete version of Laplace transformation. That is, Z transformation is used to solve a discrete version of differential equations. Laplace transformation is used for continuous function, whereas Z transformation is used for discrete sequence. Okay, let's look into the overall syllabus of Z transformation. So Z transformation, in the Z transformation, it contains definitions, some standard functions of derivations, damping rule, shifting rule, initial and final value theorems and some problems based on that, inverse Z transformations and applications of Z transformations to solve difference equation. Let's go to the definition of Z transformation. Z transform of a sequence un denoted by Z of un is defined as Z of un equals summation n equals 0 to infinity un into z power minus n, which is equal to u bar z. Here u bar z is the Z transform of sequence un and z is the complex number. Z transform exists only when infinite series is convergent, and also here the sequence un is defined for discrete values of n equals 0, 1, 2, 3, etc. and sequence un is 0 for n less than 0. Okay, let's start with the Z transform of some standard sequence. The first one is Z transform of a power n. So to solve this, we have Z transformation of un. So what is the definition of Z transformation? It is summation of n equals 0 to infinity un into z power minus an. Here I need to find the Z transformation of a power n. So replace un by a power n. So we get summation n equals 0 to infinity, in the place of un write a power n z power minus n. So summation n equals 0 to infinity a power n, if I take z power minus n to the denominator, will get a power n by z power n. And also summation n equals 0 to infinity, and we can write this as a by z power n. If I put n equals 0, 1, 2, 3, etc., we'll get a power z power 0 plus a power z power 1 plus a by z power 2, etc. Here a by z power 0 is 1 plus a by z power 1 is a by z plus a by z whole square etc. So the given thing is in the form of geometric series, that is 1 plus r square, etc. The sum of geometric series is defined as S equals 1 divided by 1 minus r. Here 1 is the first term and r is the common ratio. For this thing, if I apply this to here, we can write 1 divided by 1 minus, in the place of r, replace a by z. If I take LCM, I can write this as z minus a by z power 1. This z goes to numerator, that is z divided by z minus a. So this is the z transform of a power n. So just now we have solved the z transformation of a power n, that is z divided by z minus a. By using this, we can write z transformation of 1 power n, that is nothing but z transformation of 1. So here just replace a by 1, we get z divided by z minus 1. So this is the z transformation of 1. Similarly, for z transformation of minus 1 power n, replace here a by minus 1, that is z divided by z plus 1. So this is the z transformation of minus 1 power n, that is z divided by z plus 1. Okay. Here is the second one, that is if p is any positive integer, then z transformation of n power p equals minus z d divided by dz, z transformation of n power p minus 1. So this problem is very important in the exam point of view, and also after solving this derivation, we'll use this derivation to solve some more sequences, that is for z transformation of n, z transformation of n square, z transformation of n cube, etc. Okay. Solution. We know that z transformation of un equals summation n equals 0 to infinity un into z power minus n. Now we need to solve z transformation of n power p equals minus z d divided by dz, z transformation of n power p minus 1. So I'll take the right side and I'm going to prove the left side. So in the right side we have z transformation of n power p minus 1. So I required z transformation of n power p minus 1 here. So this becomes n equals 0 to infinity, replace un by n power p minus 1. We get n power p minus 1 z power minus n. Next we need to differentiate this with respect to z. So differentiate with respect to z. This becomes d by dz n z transformation of n power p minus 1. Summation n equals 0 to infinity, here n power p minus 1 is constant, we need to differentiate this z power minus n with respect to z. So differentiate this, we'll get summation n equals 0 to infinity n power p minus 1 into differentiation of this. It is in the form of x power n. Differentiation of x power n is n into x power n minus 1. So this becomes minus n into z power minus n minus 1. So we'll get summation n equals 0 to infinity minus, I will take outside, n power p minus 1 n power 1. n power p minus 1 n power 1 is n power p. So this is because of mathematical induction, that is a power m into a power n equals a power m plus n. and will remain with z power minus n and minus 1. So this is the d by dz of z transformation n power p minus 1. So here this part is completed. Next we required minus z in the left side. So multiply minus z on both sides. We'll get minus z d by dz is z transformation of n power p minus 1. So multiply minus z here. Already we have minus, so minus into minus it is plus z summation n equals 0 to infinity n power n z power n power p z power minus 1 n minus 1. Multiply this z to inside, we'll get summation n equals 0 to infinity n power p into z power, again z power 1, z power minus n minus 1, z power minus 1 plus 1 will cancel with each other. So we'll get z power minus n. See the definition of z transformation. Z transformation of un is summation n equals 0 to infinity un into z power minus n. So I'll take this as equation 1. I can write by using equation 1 this as z transformation of n power p from 1. So this is the required result. So next one, z transformation of n which is equal to z divided by z minus 1 whole square. We need to prove this. So to prove z transformation of n, we need to require the result of the previous problem, that is z transformation of n power p. Just now we have solved this problem, that is z transformation of n power p is minus z into d by dz into z transformation of n power p minus 1. So I need to prove z transformation of n. So we have z transformation of n power p. So simply by putting p equals 1 we'll get z transformation of n. So this becomes z transformation of n equals minus z into d by dz z transformation of n power p minus 1. So if I put p equals 1, 1 minus 1 is 0, n power 0. So n power 0 is nothing but 1. Next, minus z into d by dz z transformation of 1. What is z transformation of 1? Just now we have solved the z transformation of 1 power n, that is nothing but z divided by z minus 1. So 1 power n is 1 only. So this becomes z transformation of 1 becomes z divided by z minus 1. Next we need to solve this. We need to differentiate z divided by z minus 1 with respect to z. It is in the form of quotient rule. What is quotient rule? It is u by v, denominator square, denominator into differentiation of numerator minus numerator into differentiation of denominator. So here u is z, v is z minus 1. Apply this quotient rule here. We'll get minus z into u by v, denominator square, that is z minus 1 whole square. Next, denominator into z minus 1 into differentiation of numerator, that is 1, minus numerator into differentiation of denominator. Differentiation of denominator is z minus 1. So differentiation of z minus 1 is 1 only, and the differentiation of 1 is 0. So here we have plus z and minus z. This will cancel with each other. Next we'll remain with minus z into minus 1 divided by z minus 1 whole square. So multiply this minus z to inside, we'll get z transformation of n equals z divided by z minus 1 whole square. So this is the required result. And the next one, fourth one, prove that z transformation of n square, that is z square plus z divided by z minus 1 whole cube. So as we done in the previous problem, we know that the z transformation of n power p is minus z dy dz, z transformation of n power p minus 1. Again replace p by 2. Replace p by 2. We'll get z transformation of n square minus z dy dz, z transformation of n power p minus 1. So n power p minus 1, 2 minus 1 is 1 only. So we'll remain with z transformation of n minus z d by dz into z transformation of n. So what is z transformation of n? So z transformation of n is z divided by z minus 1 whole square. So we need to apply this here, that is z divided by z minus 1 whole square. So next we have to differentiate z divided by z minus 1 whole square with respect to z. So this is in the form of quotient rule, that is u by v method. U by v method means minus z into, again as I solved in the last problem, z minus 1 whole square. Z minus 1 whole square becomes z minus 1 power 4, denominator square. Next, denominator into differentiation of numerator, differentiation of z is 1 minus numerator z into differentiation of denominator z minus 1 whole square. Differentiation of z minus 1 whole square is 2 into z minus 1. Next, minus z into, here we have z minus 1, here also we have z minus 1 whole square. So take z minus 1 common, will remain with z minus 1 minus 2z divided by z minus 1 power 4. So z minus 1 z minus 1 will cancel. So we'll get minus z into z minus 1 minus 2z. So z minus 2z, it is minus z minus 1 divided by z minus 1 whole cube. So multiply this minus z to inside, we'll get minus z into minus z, that is z square, minus z into minus 1, that is plus z, divided by z minus 1 whole cube. So this is the required result, that is z transformation of n square. So next problem is, what is the z transformation of the sequence n cube? So z transformation of n cube is z cube plus 4z square plus z divided by z minus 1 power 4. So as we know, z transformation of n power p is minus z d by dz, z transformation of n power p minus 1. Again replace p by, so here we have n power p, here we have n power 3, so replace p by 3. We'll get z transformation of n cube, that is minus z d by dz, z transformation of n power 3 minus 1, that is 2, z transformation of n square. So minus z d by dz into z transformation of n square. What is z transformation of n square? Just now we have solved this one. It is z square plus z divided by z minus 1 whole cube. Next, Again we need to differentiate this z square plus z divided by z minus 1 whole cube with respect to z. It is in the form of quotient rule, that is u by v method. So u by v method means denominator square means z minus 1 power 6 denominator square. Now it is in the form of a power m into n, that is a power m into n, mathematical indices. That's why we have written here z minus 1 power 6. Denominator into z minus 1 power whole cube into differentiation of numerator. So what is the differentiation here? Z square 2z plus differentiation of z 1 minus numerator z square plus z into differentiation of denominator z minus 1 whole cube. It is in the form of x cube. Differentiation of x cube is 3x square. So z minus 1 whole cube is 3 into z minus 1 whole square. So here we have z minus 1 whole square, here we have z minus 1 whole cube. So take z minus 1 whole square common, will remain with z minus 1 into 2z plus 1 minus 3 into z square plus z, overall divided by z minus 1 power 6. So z minus 1 power 2 and z minus 1 power 6 will get minus z. So this becomes z minus 1 power 4. So cancelling of z minus 1 whole square and z minus 1 power 6 is nothing but, it is in the form of a power n, it is nothing but a power m minus n. Z minus 1 power 2, z minus 1 power 6, this becomes z minus 1 power 2 minus 6, that is minus 4, and thus come to denominator. That's why I have written here z minus 1 power 4. So this becomes z minus 1 into 2z plus 1, z into this 2z square plus z minus 2z minus 1, and this is minus 3z square minus 3z. Next, minus z into, here we have 2z square, we have here minus 3z square. So 2z square minus 3z square will get minus z square. Next, minus 2z minus 3z is minus 5z plus z is minus 4z. Next, minus 1 divided by z minus 1 power 4. So multiply this minus z to inside, we'll get minus z into this z cube minus z into minus 4z, that is 4z square minus z into minus 1, that is plus z divided by z minus 1 power 4. So this is the z transformation of n cube. So far we have done the z transformation definition, that is z transformation of un equals summation of n equals 0 to infinity un into z power minus n, and z transformation of a power n, that is z divided by z minus a. By using this we have solved z transformation of 1 power n, that is z divided by z minus 1, and z transformation of minus 1 power n, that is z divided by z plus 1, and also majorly we have solved z transformation of n power p, that is minus z into d by dz, z transformation of n power p minus 1. So by using this result, we have solved z transformation of n, that is z divided by z minus 1 whole square. Next, z transformation of n square, that is z square plus z divided by z minus 1 whole cube, and finally z transformation of n cube, that is z cube plus 4z square plus z divided by z minus 1 power 4. In the next class, we are going to prove some more properties on z transformations and some problems based on those properties.